So, what really happens if you fall into a black hole? It's the ultimate one-way trip, a journey with absolutely no return ticket, and for decades it's been one of the biggest, most mind-bending questions in all of science. Today we're going to take that journey together and see what modern physics predicts for this ultimate fall.
For as long as we've even known about black holes, scientists have been completely obsessed with what lies inside. It's been the stuff of science fiction for sure, but it's also been the playground for some of the most advanced theoretical physics out there, all trying to map out this impossible trip.
Well, it turns out new research is painting a picture that's even weirder and more fascinating than we ever imagined. So you're going to want to buckle up for this one. All right, let's do this. Picture it, you're an astronaut. You're just drifting closer and closer to a black hole. The first major stop on this trip? It's a place called the event horizon. Okay, so the event horizon, this is the real deal. This is the ultimate point of no return. The second you cross this invisible line, that's it. There is no turning back. The gravitational pull becomes so unbelievably strong that not even light, the fastest thing in the entire universe, can get out. You are officially all in on this journey.
And right away, things start to get, well, let's just say a little uncomfortable. You've probably heard of this famous concept, spaghettification. And it's not just a funny word. The gravity pulling on your feet, which are just a little bit closer to the black hole center, is exponentially stronger than the gravity on your head. And the result? Your body gets stretched out, thinner and thinner, literally like a long piece of spaghetti.
So, somehow you've survived being turned into cosmic pasta. What happens now? Well, this is where the older theories, the ones based just on general relativity, started to get really, really wild.
And I'm not talking about some sci-fi fantasy here. These were actual outcomes predicted by our best models of black holes. I mean, you could theoretically pop out somewhere else in the universe through a wormhole, see the infinitely dense core of the black hole, or even travel through time. The big, glaring problem? All of these things seem to completely shatter the fundamental rules of physics as we know them.
Yeah, exactly. As GLA graduate student Tyler McMakin puts it, it was just a bunch of things that go against what we think should be physically possible. And for physicists, that's a huge red flag. It meant that a massive piece of the puzzle was just missing.
And guess what that missing piece was? It turns out it's quantum mechanics. The moment you add quantum effects to the equation, the entire journey changes. Forget the wormholes and the time travel. They get replaced by something way more intense. It all kicks off with something called Hawking radiation. Let me break it down for you. All around the black hole, in what we think of as empty space, pairs of particles and their opposites, antiparticles, are constantly popping into existence, and then poof, they immediately cancel each other out. But if a pair happens to pop up right on the edge of the event horizon, one particle can fall in while the other escapes. Now, they can't reunite to disappear. So that escaping particle, it becomes real, tangible radiation. So as you keep falling deeper and deeper toward the center, you're not just falling through empty space anymore. No, you're falling through an increasingly intense storm of this very Hawking radiation. It just builds and builds, creating this incredible amount of energy all around you. And according to the new research, this storm of energy gets so ridiculously powerful that it forms a literal wall of fire. Just as McMakin says, as you approach the inner horizon, you're met with a wall of diverging energy from Hawking radiation. And this wall, it completely seals off all those weird physics-breaking possibilities that the old theories talked about.
So, hitting a wall made of pure, infinitely diverging energy, what in the world would that even feel like? Well, the forces that are happening here do something completely opposite to what you felt at the beginning of your trip. So think about this incredible shift. You start out with spaghettification, right? Where gravity is stretching you out. But as you get closer to that wall of fire, all those energy waves from the Hawking radiation get compressed or blue shifted, squashing together with unbelievable power. This new quantum force completely overwhelms gravity, and instead of being stretched, you get flattened. And yes, researchers have jokingly started calling this pancakeification.
This insane squashing effect leads to one of the absolute weirdest concepts in all of physics: negative temperature. Okay, stick with me here. We usually think of temperature as just the random motion of particles, but in this case, the energy is so incredibly high and so perfectly ordered that the system behaves in a way that is mathematically less than absolute zero. It's a state that's, in a weird way, hotter than infinity. It sounds impossible, but it's a real prediction from these models, even if we're all still trying to wrap our heads around what it truly means.
All right, so you've been stretched into a noodle,
flattened into a pancake, and blasted by a wall of fire. Your journey is almost over. You have finally arrived at the singularity.
That quantum wall of fire doesn't lead you to some magical wormhole. Nope, it's the final gate before you hit the singularity itself. And as McMakin explains, this isn't just the end of your trip. He says it marks the end of space-time as we know it. Just like the Big Bang, it's a point where our current laws of physics just stop working.
And that leaves us with the ultimate question. The quantum effects, they solve the old paradoxes of time travel and wormholes, but they leave us with an even deeper, more profound mystery. If you reach a point where space and time literally cease to exist, what comes next? What begins? That, right there, is the next great frontier for physics to explore.